Hello and welcome to Calculus 1. I know, it's so exciting. First day, and it's a late start, so we are clear, right? It's public. So we are going to first take a look at the pre-calculus. Here's me spelling it with K's. Pre-calc review, where we just take a look at the important aspects of pre-calculus which we need to survive, right? So calculus consists of three major ideas: limits, derivatives, and integrals. And all of those are applied to functions. So if you don't know what functions are, you're technically doomed, right? So calculus, yeah, I spell it with C's, damn it. So calculus has, number one, limits, and we are going to start talking about those tonight. So you will have a limit of f of x as x goes to a. We have in calculus derivatives, which will be, let's say, d dx of f of x, and then three integrals. Integral of f of x dx. So these are the three topics. All of these are covered in Calculus 1, where majority of integration is also covered in Calculus 2. Calculus 3 is all of these concepts from scratch in 3D environment. So you are not learning too many new concepts there. You're just modifying whatever you have to modify, working with vectors and vector valued functions for this to work in 3D. So that's it. Now we are observing here that all three of these have f of x, which is the function. And clearly, you must know what the function is in its purest form, so you can use it. So here's the definition. Function is a rule which assigns to each x in the domain a unique y in the range. I am going to underline four important words: rule, domain, range, and then the word unique. Note that unique is underlined twice. Now, to define these words, the word rule is the formula, like y equals x squared plus 3x minus 1, all right? So a rule refers to a formula, but you can also put any formula from physics or engineering. You can put in any formula from chemistry, whatever. It's a mathematical rule that you can, compute things. So rule has nothing to do with the function. Rule is just the formula. Then you have domain, which is set of all input values. Range, set of all output values. And then the word unique, which is actually what makes this definition a function definition. The word unique can be taken out And if you take the word unique out of this definition is no longer a definition for a function, but a definition for mathematical relation. So it is the word unique which makes something, which makes this definition of a function. Now, when you are thinking about mathematical functions, you see all these abstraction and all of this stuff, right? You don't really think about the most basic ideas, where you should always start. Try to always, when you see mathematical concept, try to always see its pure, simplest possible application. I will ask you, what is the function of the switch over there? And I'm not expecting you to give me formulas. I'm not expecting you to talk about numbers. I'm not expecting you to do anything math related, because you can define the function of a switch without using any of those terms. So what is the function of a switch? That's the output. What is the function of the switch? That's the output. To toggle the lights on and off. It's not just on and off. That's the output. It's to change the output of the lights. That's the function of the switch. Behold. Here is the input. See this thing? It's the input. All right? Right? So, this thing sits in a domain. These guys sit in a domain. I can use these, I can use this one, I can use my nose, right? Use his nose, right? Right there. So, a lot of things are in the domain of me using it to excite the switch, and we change the outcome. So domain is whatever you can use to operate the switch. Now there are things that you can't use to operate the switch. Give me examples of things you can't use to operate the switch. Yeah, they're ridiculous. I wanna know. Water? High power water, like okay, water, fine, sure. Like if I am to go with the bottle and just go, it won't work. Okay. But if I put it in a power washer and then just go, it might work. So we have to be. All right, fine. Oh, you can't go in and switch with water. You only have one wire that was over. No, that's fine. Anything else? Your mind. Yeah, see? Not a Jedi, huh? Sucks. All right, fine. Your mind. What else you can't use? The air, unless it's compressed air, same like water, but sure. If you go there, it won't work. Anything else? Your eyes? I've never heard that one. This is why this is always fun. Your eye, do you mean like looking at it, or you think physically take the eye out and because I don't know what the consistency is. I never tried. Anyone wants to borrow? All right. Throughout the years, I've heard so many wonderful examples, like jelly. Like, yeah, exactly. Right? It's going to be messy over there. So, yeah. So there are things that we cannot use to excite the switch. Therefore, those things are not in a set of possible input values to change the outcome of the function. You can't plug those in. Output is clearly lights off and lights on. The rule is that you have to push the switch in order for change to occur. And hopefully you see that all of these concepts are separated. There's a whole bag of things that you would use to push against the switch. The concept of a rule is what needs to happen to a switch for us to get the outcome. The range is the outcome, lights are on or lights are off. And then finally we get to the word unique. This switch is wired to these sets of lights. So when I push this switch, I don't have to worry about this switch turning lights on and off in a hallway, in my house, on a Falcon Heavy, right? Because this switch is uniquely wired to work with these lights. Now, if I change the wiring, well, in that case, I changed the rule on which lights are controlled by this switch. If anyone has a remote starter for a car, we can actually take that remote starter apart, and instead of the little switch that you use to press on it to turn the car on, you can wire this switch. In which case, when you push this switch, it will start your car, but it will not work with lights. So the idea of a function is that you are going to have some kind of an input. The function will change that and give you some kind of the output. We have the notation as y equals f of x, and as an example we can take a look at f of x being 3x squared minus 4, and then we want to calculate f of 2. Well, if I'm replacing x with 2 on the left hand side, I better replace x with 2 on the right hand side and get exactly. So 12 minus 4 is 8. So 2 is the input. This over here is your rule being applied, and 8 is the output. We know that we can put that as ordered pair to 8, and then eventually we can place that on the graph, right, as a point in space. In this case, two-dimensional space. So we have this correspondence between the input, output, and the rule, which is the function which changes. Now, we also have certain functions where some numbers are not welcomed, which means the domain is not all real numbers. You can't pick anything you want. For instance, a function f of x equals square root of x minus 3. Right? You are only allowed, for the domain, you are only allowed to pick x's that are bigger or equal than 3. Because if you pick anything less, you are not going to get the real number. Because we know that the square root of a negative number is not real. It's going to be imaginary, right? You also have a function such as f of x equals, let's say, 2 over x plus 3. Let's not use 3 all the time. How about 6? Over here, domain is everything except negative 6. Negative 6 is not cool because if you plug in negative 2, you are going to get 0 in denominator, and yeah, there you go, explosion. So we have restrictions with functions. Not every number will be okay to be used all the time, and that depends on the situation, right? So in terms of our switch, there are certain things that you can't use, like an egg. You can't use egg to press because it's going to break. Can't use jelly. Can't use the moon, right? And don't kid yourself with the thing when they, in Despicable Me, they shrink the moon and they steal it because it doesn't work. Gravitational pull on such a compression, right? You should calculate that on your own. You still have all the mass. You won't be able to carry it around. So you have set of numbers that will work and set of numbers that will not work. And then you have those nice functions like polynomials. When anything you throw at it, it works, right? Positive number, negative number, 0, they all work just fine. So once we understand the function at its core, understand that the function is just going to give us the y value once we compute the input. Once we understand that you can use the functions to model the world, we can start working with operations with functions so that we can combine functions in some sense to get new functions out of old functions. So now we can add, subtract, multiply, divide functions. We can square them, and square root the function, do all of those cool things. And then you can also do function composition, which is one of the most important things that you must know for this class, otherwise you're doomed. So again, function is going to give us some type of an answer. So let's say you have f of x to be x squared minus 3 and g of x to be x squared plus x plus 1, right? So now I can ask you, what is the f of 5? Well, you will say 25 minus 3 is 22. And over here, g of 5, you will say 25 plus 5 is 31. Now, I can ask you, what is f plus g of 5? Since you calculated each one independently, you can just add those answers and get 53 and be done with everything. But then you might be skeptic, and then you say, well, okay, let me add functions first, and then plug 5 and see if I'm going to get 53. And you better. So we have x squared minus 3 plus x squared plus x plus 1 for the total of 2x squared plus x minus 2. So now as you plug in 5, you have 2 times 5 squared plus 5 minus 2. It works out to be 25 times 2 is 50. 55 minus 2 equals 53, which is exactly what we had to get. Otherwise, we broke mathematics, we can go home. Now, if this works for addition, it's going to work for subtraction, multiplication, division, provided that the bottom is not 0, squaring, and all other operations that we have. This is the way to create new functions from old. But then there is this one way to combine functions that for us is more important than even the ones that I listed. And that is function composition. Function composition takes one function and plugs it into another function. Let's immediately take a look at the example that you are all familiar with. You have some kind of a bag, with you, whatever kind of bag, and then you have keys. What's a function of a car key? What is a function of a car key? Great. And what is a function of a bag? To put stuff in it. Can you have a key that has some kind of function plug into another object that has a different kind of a function? Right? Now, I'm going to replace keys with computer, and we'll forget about the key example at all. Actually, we can keep keys. Yeah, let's keep keys. The reason is you're going to get your bag to be stolen while it's empty, and get it stolen with either keys or computer in it. In which case you are much more upset when the keys or the computer are in it, right? So sure, everyone is going to be upset if the bag is gone. But if the bag was empty, you are less upset than if your bag contained either a computer or keys and then it was gone. So we have to be clear on that. And if you are equally upset for both, then there's something seriously wrong with you. Right? Perhaps you should check it out. The idea is that the function of the bag doesn't change whether you put keys in it or it's empty, right? The value of it changes, right? So you have an external object that also has a function to it, plugged into a bag, which has a function, and then the entire situation changes depending on what you put in it. You can have a bag with keys, bag with a computer, bag with a book, bag with a sweater in it, and every time you switch the type of the object that is in the bag, which is the other function that you're plugging in, the entire system changes its value and changes its function. For instance, your bag now contains books, computers, and notebooks, and pencils, and things because you are coming to class. If you are going camping in 3 weeks and you are bringing the same bag, if you pack books, computers, and other things that go camping, again, wrong thing, right? So the outer function, right, the function that you're observing from the outside can remain the same, but the value of that function changes when you plug in a different, smaller function inside. So that's what the function composition is. Now we are going to describe this particular concept from around us mathematically. I'm going to have a function f of x, which is, let's say, x squared plus x minus 2. And I'm going to have another function g of x, which is, let's say, square root of x plus 1. Now what I'm going to do is I'm going to plug function g into f. And mathematical notation for that is f composed with g of x or f of g of x. So this is the function composition. And looking at our example above, you are going to take f and replace its x with g of x, which is f of square root of x plus 1. This notation means that you are supposed to change every x of f with g. Are you following the sentence? This notation means that every x of f needs to be replaced by entire function g. Great. What is the f? It's x squared plus x minus 2. Every x needs to be replaced by g, so square root of x plus 1 and square root of x plus 1. Get rid of unnecessary parentheses and perform algebra if you can. Square root is going to be killed by a square, giving you x plus 1 plus square root of x plus 1 minus 2, and everything together is going to work as x minus 1 plus square root of x plus 1. Observe that the function at the end doesn't look like any of the input functions. Sure, it has this component of x plus 1, square root of that, but this function is not a polynomial because it has a square root. Over here, f is polynomial. This is a radical function. Well, this is not a pure radical function because this is not on the radical, right? So you see that we took two, if you want to call them pure functions. You have a radical function, you have the polynomial, and we combine them through this function composition to obtain a completely new type of a creature that we didn't have so far. And now we can talk about the specs of that new created function in terms of domain, range, increase, decrease, and everything else that we might have to look at. Now, we can also compose G with F, where G is the boss, as I say, and F is plugged in. So now this is still function composition. And in terms of our example, we have to take function G and plug F in it, which means is G of x squared plus x minus 2. So that means the square root of x plus 1. And your x now is replaced by x squared plus x minus 2. Well, your function composition now is just the square root of x squared plus x minus 1. Ta-da! That's it. That's the function composition. How important is this on a scale 0 to 10? It's at about at 12. Most of the derivatives that you will be dealing in this class with and your next classes in terms of pretty much every other course are going to be chain ruled, which is the derivative of this. You're not going to deal with sine x, but you're definitely going to deal with a sine 3x, sine x squared, right? And all of those are function compositions. And then in integration, the most frequent method of integrating is U substitution. This again. So there will be a lot of function composition, and if you're not comfortable with this, get comfortable very fast. As a friendly suggestion right there. So you can find some lectures. Now we're going to do a few examples to illustrate the skill that we need for these. These are just basic of composing things we need to decompose in this class. You had hand or read your mind, answered it as you were, right? Good. I tend to do that. So I mentioned the skill that you need is not to compose functions, but to decompose functions. And that's what we need to know. So if I am to give you a function, y equals, let's say, sine squared of x. I would like to know what's function f, what's function g, so that when you compose f with g, you get sine squared x. In other words, I'm asking you, what is the outer function and what is the inner function, so that when they're composed, you will get sine squared x. Would anyone like to take a stab at this? Tell me what's f and what's g. All right, so we see where the skill is, right? The answer to this question needs to be instantaneous for 100% of population in this class. If you are to go past 3.6 in this book ever, right? And this book ends at 6.2. So you can kind of survive the first half of the course, and then that's it. And don't even think about Calc 2, 3, or anything else. So what are we having here? We have a problem where we have to do completely backwards of what you used to from composing functions, which is this example and example above. So you have to step back and look at what's the overall function. Would anyone still like to try? Tell me f is equal to... Beautiful. And g is? Sine x. All right. What? How? I know, right? So we get to rewrite this sine as sine x, everything squared. And all of a sudden now, it kind of makes sense to have the inner function replaced by g of x. So now you see this g of x squared, which kind of reminds you of x squared, where x is replaced by sine x, and all of a sudden these things start making sense. It takes time. It takes a lot of practice. And do a lot of practice this weekend so you can operate on the level. Let's do another 5 examples.
Question.
Yes?
Is sine squared times x equivalent to sine x squared?
Nope.
So
Because sine, without the argument following it, does not mean anything.
right, so I don't really understand sine squared.
Well, that's why I rewrote in the second line that it's actually that square, you can put the parentheses around. So when you write sine squared x is the same as sine x everything squared, the meaning of that is sine x times sine x. If you write sine x squared, the meaning of that is sine x times x. And they are much different creatures, as you can see from. So I'm just going to say these two not the same. Now we are going to have the same notion once we see in this class ln cubed x. Ln cubed x means ln x cubed, which is ln x times ln x times ln x. To be completely contrasted by ln x cubed, which is just ln of x times x times x, which has again nothing to do with the line above. Again, not the same. So I'm hoping that this notation is now making sense.
That's just the convention that's accepted in math. This sine
The
square x
Square over here?
times sine, yeah. It's like a shorthand.
Yes. Well, you have that if you just have x times x times x, right? You will call that x cubed as the exponential. So if you have a flower times a flower, right? It's going to be a flower squared. It's the mathematical notation that we use for repeated multiplication. I should have used hearts because Valentine's Day is coming up, also known as the Singles Awareness Day. Heart times a heart equals heart squared, right? So it doesn't matter what this object is. you can have that object to be a number, meaning 3 times 3 times 3 is 3 cubed. You can have it to be a variable, x times x times x. Sine times sine times sine. You can have even the entire structures in terms of the whole integral or whatever can be squared.
But the reason it throws me is because sine's just like an operator. Without an argument, it's not a value that can be squared. So
exactly. That's perfect. Yep. So it's just a notation. It's a shorthand notation because we don't have to put the parentheses, and then square is not close to x, it's before x, so you don't get to confuse it with this too much. You see how I can see a student confusing these two, and that's a big problem. It's a huge problem. So I am actually welcoming of this notation because I am a visual learner, so for me, this notation, in contrast to this, is much more powerful than if I am trying to contrast these two. Because we are used to, 3 squared and 3 squared being the same thing. But if you do that on a sine, hell breaks loose because it's a completely different concept. So, and you see it repeated underneath with the ln, and it will hold for technically everything else. Yes?
When you took out the f and the g, you had x cubed and the sine of x. Would that be like sine x cubed? Why would you just say just sine for g?
Hold on, Conrad, what are you talking about? Which?
Right before you did the last thing?
This one?
Yeah, the f you said is x squared, and then you had the g sine of x. Wouldn't that, if you put them together, wouldn't it be x cubed?
No, why?
Like an x times x squared.
You are replacing. You are replacing. You see, when you are computing a function, see, f of x is x plus 5, and you want to compute f of 3. You have the rule, and you are replacing this x by 3, and you get 8. So now, with our example, if I have that f of x is equal to x squared and g of x is equal to sine x, I am going to, for composition, I'm going to write x squared, and then I'm going to replace x with sine x, and then I'm going to put this square there so it's, right? So you don't create another x out of nowhere, because every x is replaced by entire g. And we're going to do the difference quotient very soon, which is a central piece for our derivatives. Another example, I would like you to decompose function y equals 3 over x plus 5. So let's see what you can master here. So again, what is f? What is g? Yes, you have it?
F is 3 over x, and g is x plus 5.
Okay, what do you have?
I was going to say f is 3, and then g is x plus 5.
3 over x for f, 3 over x, and x plus 5 over here. And I'm just going to circle this x, and I'm going to tell you that this x is taken out and replaced by g, which is x plus 5, and you actually visually get what you need. Bueno? So, gets replaced by g equals x plus 5. and you have the answer. Nice. Let's get a spicier example. Y equals 4 cosine squared x cubed. What? Right. We're working on that. I just got to. Oh my God! We had to move. Yeah, no, we had to move because projector died. Hi, everyone. This is Ali. She will be the TA for the class, supplemental instructor. Now that she's standing here and getting red in the face because of talking about her. So Ali is in honors college and took my Calculus 1 class and survived it with the average of like 207. She has been extraordinary help in other classes as well. Hopefully you guys will come to her sessions and learn more. She will be able to help with things that I will not help with, like labs. It's graded material, right? I'm not going to tell you whether it's right or wrong before you hand it in, because why grade it afterwards, right? Project, another one of those graded materials. Homework, I will always answer in class 100% of the homework, but Ali can also help with homework, and then also with concepts, right? If you miss the class and for whatever reason my office hours are not working out for you, even though I have 5 a week, Ali can help with that as well. So you have something to say?
Yeah, so I do 2 of Nick's Calculus 1 classes, and I was talking with the other class, and it seems like the majority was able to meet Thursdays from 12 to 1. I don't know how many of that accommodates. I could hold another review session too, and have 2 review sessions in 1 week. Just quick raise of hands who's able to do Thursday from 12 to 1. Okay.
6. Ali's in an extreme rush now because she's having organic chemistry class.
So
yeah, she's in organic chemistry class, so she's on a break now. She's just like in and out.
Yeah, and I emailed her about the room number. I'm waiting to hear back, and then I'll send you guys an email.
Yes. You can reach Ali through the email.
Yeah, I put my email on.
Well, it's on the list on Lions Den.
Okay, yeah,
when you go on the Lions Den and you click email, you will have the email, like the name for everyone in the class roster, and then Ali under teaching assistant and myself, right? So you can just check off Ali and send email directly to her.
Yeah, and I can make slips to possibly give to them. Just what days work for them best.
Sure.
And then you could give them to me. Or everybody could write it down now. What days?
Well,
I should write
you
schedule.
have the schedule and all of those things. So
I
we can do it on. Yeah. We can do it on. Today's what? Thursday, Tuesday.
I could email you a document because I have Orgo Lab.
Oh yeah, you also have. Okay, good. Sure, we'll deal with that. Great.
Okay, I gotta run.
Run.
Bye, guys.
So it's
Have a
run
great
back.
class.
All right, so she will be the great resource because, as I said, she was in my class, in my Calc 1, Calc 2, so on, and did extremely well. She knows my exams, she knows the way I work, the way I think, and she will tell you all the things that I will not. So hopefully you guys will utilize. And it's just an extra, and it's obviously offered to you for free. Very few sections have these because very few of us instructors apply for these supplemental instruction and so on. We'll talk more about this. Now, did anyone crack the code over here? What do we have? How many functions are all pushed together? 3? Sounds good. Can we push it to 4? I don't know. Let's see. Now, I can rewrite this as y equals 4 times cosine x cubed everything squared. And now I'm going to ask you, do you see that x cubed is plugged into cosine? Right? So I'm not going F, G, H. Let's see if we can fit everything with 3, right? So H. If H is x cubed, right, because that's this most inner piece, then x cubed is plugged into cosine x to create cosine x cubed. And then cosine x is plugged into 4x squared. Ta-da! Yes?
Why couldn't it be just f and g cosine x cubed e g of x?
Because that is a function composition of 2 functions, x cubed and a cosine. One is a polynomial, one is trig. Fair? Excellent. Yes?
So we're just assuming that top down, left, right for the composition.
Yes. Some people like to think of this as the layers of the onion, right? So you have the most inner piece of the onion to be x cubed, and then you have cosine x, and then you have finally 4x squared. Now, if you want to compose this, you take x cubed, replace this x by x cubed, you get cosine x cubed, and then you take that and you plug it for this x and you get 4 cosine squared x cubed. So it's very quick to check. I understand that this might be a little bit tricky because you haven't done this in your pre-calc class, but as soon as you practice a function composition, function decomposition should kick in at some point when you have enough experience with the one that you did in class. Now, you might be going, but why? Right? Well, I told you, 90%, 95% of our derivatives are going to be chain rule derivatives, which are derivatives of function composition. If you can't decompose function mentally, you will have a lot of trouble with that. And that's technically half of your course. Section 5.5, the most important integration technique is backwards chain rule, which is U substitution, which is this stuff again. So moving into Calc 1, clearly knowing what's a function, what's not a function, extremely important, and then function composition right after that. The last piece on function composition that we need to understand and have is the difference quotient formula, which you were forced to memorize in Prekalk 1, do some problems, and then you move on with your life. Well, welcome to Calc 1, when difference quotient is a part of one of the most important definitions in Calculus 1. So you are used to difference quotient to be given by f of x plus h minus f of x divided by h. And in Prekalk 1, in our infinite wisdom, we ask you to compute difference quotient for function whatever. Let's see. So say f of x is equal to x squared plus 3. You are supposed to compute difference quotient for this. All right. As you're looking at the formula, you have three parts. Function composition part that you have to find. Vanilla f of x, which is already given, since I call it vanilla, all right? And you have this h on the bottom, which you will just copy. So three parts to the formula. So again, f of x is already given to you right here. So we are going to use function composition to create f of x plus h. This notation here is telling you that you are supposed to change every x of f with x plus h. So I'm going to remove x and put x plus h and square it, and then just add 3. Now expand. X squared plus 2xh plus h, and then plus 3 at the end. So what's the difference quotient equal to? DQ stands for difference quotient, not Dairy Queen. They stole it and no one sued them, right? X squared plus 2xh plus h plus 3 minus x squared plus 3, which is f of x in parentheses, divided by h. Great. Get rid of the parentheses. Cancel what you can. And observe that only the terms with age survive. You can factor out age, have 2x plus, oh, this is h squared over here, plus h divided by h. Now age cancels, and you're getting 2x plus h. So what is the difference quotient for x squared plus 3? The difference quotient is 2x plus h. Now, big deal, right? Yeah, because when you put a limit in front and send h equal to 0, this 2x becomes the derivative of x squared plus 3. And all of a sudden becomes the central idea of Calculus 1. So yeah, pretty big deal. Get used to these calculations quickly. So what you see here is about 95% of your 3.1 problem, section 3.1. You put the limit in front, and from this point on, you have one more calculation, and that is to send h to 0 to get the derivative of the function. So we'll see a lot of these difference quotient calculations in chapter 2 and in chapter, well, just section 3.1. After that, we're going to learn shortcuts, so you won't have to worry about the difference quotient past that point. It will be back in chapter 5, but. So that's the difference quotient. Formula that you must know right here. And then the way to compute, this is given. This is what you find, plug everything in where they belong, massage the algebra till you get 2x plus h, and you're good to go. Fair? Good. Remember how there are no graphing calculators in calculus courses, and that is Calc 1, 2, and 3? And I talked about the pushback of universities and everyone everywhere. It's a zero calculator policy. You can't bring even the solar one in to calculate, I don't know, 39 times 7. So you have to know how to graph. And for that, you either have the knowledge of Prekalk 1 to graph the functions, which is section 1.6 in the Chili Pepper book if you have it. Or you will have to waste incredible amount of time to compute points and then connect the points and hope to see the graph. So now we're talking about graphing. Graphs are a central piece of mathematics. It's a visual representation of your equations, formulas, functions. We can read the graph faster than anything else. Instead of the graph, you can look at the table of values, but it's much harder to follow table of values than a line that is going up or down. So you have certain graphs that you absolutely must know, like the constant graph. Say y equals to 3, which is just a horizontal line through 3. You have to know linear graph. Y equal mx plus b. That will be some kind of straight line. You have to know quadratic. Y equal ax squared plus bx plus c, or whatever other equivalent form. Oh, here we go. This is what I was telling you about, that when software gets tired, it starts erasing stuff that I write. No coughing. So I guess I'll have to, I hope it doesn't, yeah, see, it did. Well, I'll have to go and fix the notes eventually. Okay, so after that, there is cubic. Let me just see something. There is no save option. Okay. Cubic. Y equal x cubed is the basic one, which is just a squiggle through the origin. Rational. 1 over x. With a vertical and horizontal asymptote. Radical. Y equals square root of x. So constant, linear, quadratic, cubic, these are all polynomials. All right, exponential. We can go with e to the x, but obviously any other base is fine. Going through 1. Logarithmic. I'll just do ln x. But then again, any other base is fine. Going through 1. So these are all default basic functions. 6 trigonometric functions. Yay! Sin x. Let's do the trig. Sin x. The principal wave starts at the origin. Cosine x starts at 1. Tangent x looks like a cubic, except it has the vertical asymptotes and it keeps repeating forever. Cosecant x. For cosecant x, you have inverted sine. Take the sine graph, cut it on the middle line, pinpoint min and max, right? Values, and just flip the cups outside. Secant x is going to do the same thing with the cosine. So this cup is going this way, this cup is going this way, and then this cup is going this way, with the asymptotes wherever the cosine cut through 0. And finally the cotangent x is going to be this part, 0 to pi. These are the basic graphs. There is one more that you are going to need, chapter 2, and then later on, and that is inverse tangent. Inverse tangent graph is this. This value negative pi over 2, and the top value pi over 2. It's going to come up. These are the basic functions which you guys learned over the course of algebra for all the linear stuff and constant function, right? The horizontal line, and then quadratic, through all other polynomial ones in your Prekalk 1, exponential logarithmic in Prekalk 1, and then finally these 7 trig. I mean, there's also inverse sine, inverse cosine, and inverse these 3 constituents over here, but they're not used, so I'm not going to bother you with those. Is this it? Oh, there's a book out there, 2,500 pages of mathematical functions when polynomials are taking half of one page. And over here, polynomials took 4 spots: constant, linear, quadratic, and cubic. So, yeah, there's a lot more. We're technically not covering anything. Also, in Calc 2, section 610, you are going to learn hyperbolic functions. Another important feature that you will use a lot in differential equations. So there's a lot of these functions coming up. Now you might be looking at this list and going, oh, do I really have to know all of this? The answer is yes, because these are the basics of functions, the ones that are used most of the time. These are not special in any way, and hopefully you are seeing that the absolute value is missing, because we have a whole spiel on that, which is separate from the basic thing here. Now, what I have issue with is the way the whole curriculum works, and that is that you learn constant functions, and then linear functions, and then quadratic, and then cubic, right? And then learn this most important 1.6 section of how to move and shuffle these functions around, and then we'll go back to learning new functions, right? Without too much connection. The section 1.6 on transformational functions is exactly what the title says. transformation of functions, regardless of what the function is. If you learn how the transformation of a function works, I can give you any function that you have never seen before. You should be able to shift it and move it around because you know 1.6. By the way, 1.6, 1.7, 1.8 from your pre-calculus book are the sections that you need to know to actually be successful in anything. That's the section on function composition, section on graphing and shifting functions, and a section on inverse. So those three sections. If you have the chili pepper book still from a pre-calculus, take a look at those three sections. If you do not, library, tutoring center will have the book. Take a look at those three sections so that you are comfortable with these things, especially that you don't have graphing calculator to survive this. So what is this Prekalk 1.6 business? Well, it tells you that if you take a function f of x and you add or subtract a constant to it at the end, what you do is you shift function up or down. At this point, it doesn't matter what function you have. When you have plus 2 added to the entire function, the function simply goes 2 units up. So I don't care if it's a square root, I don't have it's e to the x, whatever you have, it's going to go 2 units up if it's your function plus 2 at the end. You have f of x plus minus c, which is going to shift everything left, right. And it's minus that shifts it, it's a plus that shifts it to the left, and minus that shifts it to the right. You can make function twice as tall or 3 times as tall by multiplying it times 2 times 3. Hopefully you remember the amplitude talk in your Prekalk 2 trig class, where you say that you can make the wave twice as tall if you go and say 2 sine x, right? Well, that's that. So now we have a vertical stretch or a shrink, because you can put the half and you are going to shrink the function vertically. So this is the vertical stretch or shrink. You also have the horizontal one when you multiply x within the function, and that one is going to be the horizontal. That's going to be the period, changing the period of your sine and cosine function. Stretch. There's a T there. And finally, you can reflect on x-axis and reflect on y-axis. So minus f of x reflects on x-axis, and f of negative x reflects on y-axis. And that's it. Now we walk away. These are 6 transformations that you can apply to a function and change the appearance of a function somewhat. So I can lift the entire function up or down, move the entire function left or right. I can squish it or stretch it vertically. I can squish it or stretch it horizontally. I can flip or on x-axis, or I can flip this way on the y-axis. Now, I'm going to apply on two examples, so you can see, same transformations on two different functions. So you can see the progression, and hopefully this stuff kicks in if it didn't in Prekalk 1. You need it. Say you have f of x given as 3 over x plus 5. Great. I can immediately rewrite this as 3 times 1 over x plus 5, where I see that I have CF, which is a stretch 3 times, and I have 5 left, which is f of x plus c. If you're adding, it's shift to the left. So, the default state for the function 1 over x is this. And now I have to move it 5 units to the left, which means that the vertical asymptote, which used to be where the y-axis is now going to be 5 units to the left. And this vertical stretch is not really humanly possible to do a good job at, so if we keep the same shape, we're pretty much good to go. Technically, when you multiply by 3, this point goes more inside. So as long as I am, if the point kind of shifts more in, then we're good to go. So I had two transformations here. There was a transformation that made the graph 3 times as tall, and transformation that moves everything to the left. Now I'm going to apply the same transformations to g of x, but now g of x is going to be the square root of x, so I have 3 square root of x plus 5. I have same transformations. Observe that if the top function is 1 over x in default state, the bottom function is root x in default state. So this is my root x. This is my 1 over x, right, default function. And now what I need to do is I need to make it, instead of being at the origin, 1, 2, 3, 4, 5 units to the left. And then I need to make it go taller because it's 3 times. So the amplitude of 3 is going to stretch it vertically, make it taller. And then x plus 5 is going to shift everything to the left. Are we agreeing on this? It will take some practice if you are not good with this. But you need to be able to sketch your graphs. Yes?
Set, shift, apply, 5, color 5, set again, and it's a move up.
Yes, that's my next example. Good. So now what I'm going to do is I'm going to again go with f of x, let's say, to be, let's just go with e to the x minus 2 plus 3. All right. What is this puppy doing over here? Come on.
bring it to the right.
Nice. Right 2. And what is this one doing? Hello? Thank you. You could have said it immediately. Instead of me spending calories to ask again. Like, consider me sometimes, right? This is why I'm depressed. I go to classroom, I ask a question, and it's like crickets everywhere. If you know it, just say it. So e to the x. We are going to go through 1 and go up, and that's e to the x default state. For our problem, I need to go, instead of being at 1, I need to go 1, 2, 3 units up and 2 units to the right. And when you lift this point 3 units up, the horizontal asymptote that was there at x-axis is going to go up. So this is the exponential function e to the x minus 2 plus 3. It's shifted right, it's shifted up. You label this point here as 2, 4. Same transformations applied to, let's say, logarithmic function. Log base 2, you can do ln, there's no difference, of x minus 2 and everything plus 3. Everything works the same, guys. You have your default case state. It goes through 1. This is your just log base 2x. And now you have to go 2 right, 3 up. Transformations are the same. It's x minus 2 on both of these. It's plus 3 at the end of the function for both of these. So you see that if you don't know what the default state of the function is, you are doomed to graph the whole thing. But transformations, right, are in some sense independent of your knowledge of default stages, because 2 units to the right means x minus 2 for whatever type of function you have. So now we have shift to the right 2 units, which means that your vertical asymptotes that used to be y-axis is shifted to the right, which means that the point shifts here, but we also have to shift that point 3 units up. So your log graph now looks like this. And this point that it's important, oh, come on. And this point that it's important is going to be 3, 3. I want to see if anything else disappeared. Good. So there we go. Your vertical asymptote that used to be at y-axis at x equals 0, now it's at x equals to 2 because everything is shifted 2 units to the right. And yay, that's graphing. Absolute value. So you notice that I didn't put the absolute value graph because you can actually stuff any function inside the absolute value and you need to be able to instantaneously graph it. So I teach absolute value from a different perspective than you just learn the V and then you walk away. Don't learn the V, okay? Pointless. So first off, what is absolute value? What does it measure? Distance away from the zero. Great. Now the consequence of it is always gives you positive numbers because the distance is always positive. If I ask you how far is your house from RV, what are you going to tell me? How far is your house? In miles. 15 miles. When you are home, how far is RVCC? 15 miles. It's not negative 15, right? Distances are always positive. So now to truly understand the absolute value, here we go. You have a 0, and then you have number 3. Now, you also have negative 3 on the other side. Observe this. Absolute value of 3 is the physical distance of 3 hops from 3 to 0. Absolute value of negative 3 is also 3, which is 3 hops. Now I want to do this one blue. And now I'm going to tell you that the black 3 and the blue 3 are not the same 3. Right? The black 3 is a location on the x-axis. And the blue 3 is a distance from 0 to 3. So yeah, sure, 3 is equal to 3. Fine. But conceptually, they are not the same. All right? Let me give you another example. Use these guys over here. 1, 2, 3. We all are familiar with the concept 3 guys are sitting over here, right? Now look at this. 1, 2, 3. Is this 3 the same as that 3? No, it's not. Right? That's 3 a.m. or 3 p.m. and this is 3 guys. So, go back to this now. 3 and 3, these 3's are the same concept. The red and the blue are the distance 3's, and 3 and negative 3, the black 3's, are location 3's. Now, it's so easy to just say, you know, absolute value makes everything positive and move along. Sure. At the end of the day, 3 is 3. And the concept we are using it for, well, the same is true when you're driving. Don't try this on your own. But as you're driving forward, your speedometer reads 10, 20, 30, 40, right? When you're driving in reverse, your speedometer goes 10, 20. Absolute value, right? Shows the positive speed, regardless of the direction in which you are moving your car. So now that you understand that the absolute value is a function which gives you the distance, which is always positive, you understand that your answer are always positive numbers. So now if I want to graph y equal absolute x, you're actually going to graph y equals to x. And then you will say, I can't have negative numbers. Bump it up. Bueno? And you got your V. But we're not considering only that case. Y equals sine x absolute value. What's that going to be? What's the graph of absolute value of sine of x now? Yes, thank you. You are not allowed to have the bottom piece going out under the x-axis. Nothing under x-axis as you are working with these graphs. Y equals absolute value x cubed. Now, this is not x squared, guys. It's very difficult to draw. You're drawing, there's like 100% chance that your drawing is terrible and wrong, because it might look like this, and it's not. It's not. Because the cubic function has this curvature like that. When you bring the other one, kind of curves and creates a little spiky, so it's difficult to draw. I understand, it's fine. Practice this one on your own. LNX, let me see. Go ahead, talk to people. Remember, I'm gonna go around and ask you to tell me the names of other people sitting next to you. I'm actually gonna do that. So it's time to draw and talk to people and okay, so what do we have? We have the log function that goes through 1. Not allowed to have this piece here, so that piece bumps up. So that's the graph. Creates a spike here, and it goes forever. So anything that would go below x-axis, it gets bumped up as in a mirror off of the x-axis, and that's the way you deal with the absolute value graphs. Nice. One more concept and then the break. Everyone happy? Good. Break. Or we can just go power through everything and get a break at 8:35. No? Oh, fine. Inverse. Generally, I like to think of the inverse as undo, because the principle is to change the input using function into output, and then whatever that output is, you can bring it back using an inverse. So if I have, say, function f of x equals x plus 5 and g of x equals x minus 5, f of 8 is 8 plus 5, which is 13. Now the second function, g, will take that 13, and when you plug 13 minus 5, will give you back 8. So this function over here is known as the inverse of f, because it turns the output back into what your original input was. The graphic for this would be that you have a set of domain input values, right? And then the range. The function f will take a value from x and bring it into the range, and the inverse function will undo that operation. Now, inverse always exists, but not every inverse is a function, and we have to be very careful about that. So here we go with a very simple idea. First of all, inverse swaps domain and range. In terms of mathematics, x is swapped with y. So to find the inverse for, let's say, f of x equals x cubed minus 2, you will write it as y equals x cubed minus 2, and then you will simply swap x and a y, and then you will solve it for y. So you get x plus 2 equals y cubed, and then finally y equals to cube root of x plus 2. Meaning that the inverse of x is cube root of x plus 2. So that's the inverse. It's very simple to obtain this thing. Swap x and y, apply some algebra, and you're done. But sometimes we run into trouble. When your function y is x squared, and you swap domain and range to get x equals y squared, and you apply square root to both sides, you have to put plus minus, you get now that y is equal to plus minus square root of x, and that thing is not a function. Now, what's the big deal? It's a very big deal. It's not a function. What does that mean for us in our class? Exactly, no limits, no derivatives, no integrals, because those are applied to functions, not to non-functions. So we have to address this issue that certain functions, like x squared, in an inverse will produce a non-function. So please understand that this is an inverse, all right? But it's not inverse function, right? So everything has an inverse. In terms of everyday dealing, right? Wait, what happened over here? Oh, he erased some stuff. So in terms of everyday dealing, I'm going to say, right? And then there is this, right? Bing, done, right? Do we have a magician that's going to put this together now? You get the idea, right? So this is the way you understand the inverse. The inverse is supposed to undo an operation. And you are supposed to get the result from where you started. I'm not going to attach this back to there. You say, yeah, use some tape, use some. It's not the same. I'm sorry. You break the vase, right? You are the vase or whatever. You are making a soup. The recipe is calling for a teaspoon of salt. You put a shovel, right? Clearly, no going back. Unless you're going to move your soup to a bathtub and then somehow rig the heat underneath and whatever. But the idea is that, you know, in certain cases, we can actually adjust things a little bit so that we can actually get a function through restricting the domain. I did not mention before, I should have. I was waiting for the graphing and then I forgot. A vertical align test is the test that you use to show that the graph is a function. And then a horizontal line test is the one that you use on the function to show that the function has an inverse function. So vertical line test equals test for functions in a visual domain. Horizontal line test equals test for inverse functions. All right. So here's my y equals x squared. When I draw the graph for x squared, which we know it's just this parabola, you better know that at this stage of the game, we are going to use vertical line test, which is a whole battery of these red vertical lines that will tell us that it passes vertical line test, therefore x squared is a function. To pass a test, these vertical red lines, all infinity of them, are not allowed to cut a function in more than one spot. If they cut in 2 or more spots, it fails to be a function. Now, horizontal line test tells us no inverse function in this case because it cuts through the parabola twice. You have more of these functions that do the same thing, like sin x. Sin x fails miserably Because when you do a horizontal line test, the horizontal line cuts infinitely many times through the infinite sine wave, right? So another example of this is sine x, where your wave that goes forever in both directions, when you do the horizontal line test, you see that it fails it miserably, cutting more than once, cutting it infinitely many times. So again, no inverse function. The way we deal with this, so that we can still differentiate, integrate, and do all of the other stuff with inverse trig functions and so on, we have a notion of restricted domain. Restricted domain fixes the issue. If I have my y equal x squared on a domain 0 to infinity, I get to draw only half of the parabola, and then its inverse is f of -1, just a positive root branch, because the -1 is no longer there because we cut it off. And then your inverse becomes a function. Like earlier had this branch as well because of the negative, and clearly was not a function. But now, when you restrict the domain, you get the inverse to be a function as well. So restricted domain fixes the issue, and we can have inverses to be functions where originally they were not. Trig functions now, again, same thing. So you have y equal f of x equals sine x, and you have sine x going forever. You cut at -pi/2 and pi/2, so only the highlighted part is the one you use. As soon as you use the highlighted part only, which is now restricted domain from -pi/2 to pi/2, you have, right? You will have the inverse now. Oh my God, this is still annoying. You will have the inverse. So the inverse is going to change your pi/2 and -pi/2 are going on his axis, and your -1 and 1 go on the x-axis. So you're starting here, and then it's going to end in this corner, and you're just going to have the inverse. And this line over here is sine inverse of x. So restricted domain helps you. Now you've seen the inverse tangent graph earlier. If you think of the tangent, 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 right? All of these are stacked. So the inverse of that must be this one, and then this one, and then this one, right? Clearly not a function vertical line test fails. But if I restrict my input tangent to only one squiggle, it gives us the graph we've seen before. And that takes care of the pre-calculus review. Now we need to talk briefly about the homework. So let me just stop. So we'll be back with limits after the break. Bye-bye.